Hello and welcome. Today we're diving into a really fascinating electronic repair that honestly plays out like a detective story. We've got a real mystery on our hands, a device that seems to work perfectly, but only for a single fleeting second.
So this is our central clue, the scene of the crime, if you will. A computer power supply springs to life, you can hear the fan spin up, maybe see the lights flicker, and then nothing. It just completely shuts down. The big question is, why? What on earth could cause such an instant, total failure?
And here is our victim, a pretty standard HP 180-watt power supply. Its job is incredibly simple, right? It just needs to take the power from your wall and turn it into a nice, steady 12-volt output for a computer. But for some reason right now, it can't even hold that for a moment.
Now, your first thought might be, hey, can't we just force it to stay on, by manually triggering the power supply on signal? But nope, that's a total dead end. The problem happens so fast, so incredibly fast, that the internal safety systems slam the brakes on everything before any external command can even make a difference. And that's what makes this such a tricky little puzzle to solve.
Okay, so let's dive in. Every good investigation has to start with gathering evidence, and for our electronics detective here, that means grabbing a multimeter to see what's actually happening on the inside right at that moment of failure.
And right away, we get our first major break in the case. The voltage on the main capacitor is sitting around 340 volts. Now, in a healthy, modern power supply, a key system called power factor correction, or PFC, should kick in almost instantly. Its job is to make the device way more efficient, and when it does, this voltage should jump up to somewhere between 380 and 400 volts. The fact that it's stuck down at 340, well, that's a huge clue that this critical system is just not starting up.
And here's where it gets really interesting. This isn't just a random failure, like a component blowing up. A low voltage reading like this tells us that the power supply's digital controller, its brain, has detected an error and is actively shutting everything down to protect itself and the computer it's plugged into. This isn't a breakdown, it's a deliberate lockdown. And that tells us something really important. This might not be a bug, but an intentional safety feature doing its job.
Okay, so now that we know the shutdown is on purpose, we can really narrow our search. The problem has to be somewhere in the system that reports status back to the main controller. So let's line up the components in that area. These are the potential suspects in our case.
The system we're zeroing in on is called a feedback loop. You can think of it like the power supply's own internal security system. The output side is constantly sending an all-clear message back to the brain. But if that message is wrong, or worse, if it stops coming entirely, the brain just assumes the worst and triggers an emergency shutdown.
And here they are, the usual suspects. In our lineup, we've got the TEA191T, which is the digital brain of the whole operation. Then there's the TEA1962, that's the PFC controller we were just talking about. We've also got the SY1202 supervisor chip, a TL431 voltage sensor, and finally, a couple of these 817B optocouplers. They're the messengers responsible for carrying that crucial all-clear signal. The fault has to lie with one of them.
So now the investigation really narrows its focus. Our detective starts testing each of these components one by one, looking for a single faulty reading. That one piece of definitive proof, the electronic smoking gun.
So after checking the brain, the supervisor, and the sensors, everything seems fine. There's only one type of component left on the list. Could the problem really be with one of these simple little messengers?
The component in question is called an optocoupler, and it's actually a brilliant little device. Inside this tiny chip, there's an LED that shines a beam of light onto a sensor. This sends a signal without any physical electrical connection. It creates a perfectly safe one-way communication channel between two different parts of a circuit. But what happens if that tiny light just goes out?
And this is that aha moment. While testing one of the optocouplers in that critical feedback loop, our technician gets a reading that is just completely obviously wrong. He knows right away he's found it.
And this right here, this is the smoking gun. A healthy optocoupler's internal LED, when you test it, should show a very predictable voltage drop of about 1 volt. But our suspect, it's all over the place, reading between 1.5 and 2.1 volts. That weird reading means its internal LED is broken. It's an open circuit. The messenger is silent. That critical all-clear signal was never even being sent.
So, with the culprit identified beyond a shadow of a doubt, the final step is actually pretty simple. Make the fix and see if our theory holds up.
The repair itself is pretty straightforward.
First, that tiny surface-mounted component is carefully removed. Then the contact pads are cleaned up really well. And finally, a new 817B optocoupler is carefully soldered right into place. It's a quick, precise, and thankfully pretty simple operation.
And the result is immediate and dramatic. The moment the power is turned back on, the main capacitor voltage is retested. And just look at that. It jumps from that measly 340 volts right up to 367 volts. The PFC system is now active. The new messenger is delivering its signal loud and clear.
And the final test confirms it all. The power supply now outputs a perfectly steady 12 volts. It stays on indefinitely. The fan control is working just as it should. The entire system is back online, all because one tiny component, smaller than your fingernail, was finally replaced. So the really crucial takeaway is this. In older, simpler power supplies, a failure like this might just cause the output voltage to bounce around. But in a modern, digitally controlled unit like this one, any hint of instability is seen as a critical threat. That 1-second shutdown wasn't a flaw at all. It was a sophisticated safety feature working exactly as designed. It's a feature, not a bug.
And that just leaves us with one final thought. This whole case was cracked just by finding one silent messenger in a really complex system. It really makes you wonder, doesn't it? How many of these tiny, invisible electronic guardians are constantly running self-checks inside the devices you use every single day?